everyone. This is Dr. Bharat Vinjamuri from Global Academy of Technology. In today's video session, we'll be discussing about dynamic analysis. How to apply the finite element method to determine the natural frequencies and the modal shapes of a structure under dynamic behavior. This video session covers the basic introduction of dynamic analysis. Also, we'll be discussing about the different types of vibrations as well as the different types of dynamic analysis. The session will mainly concentrate on determining the natural frequencies of a system along with determining the eigenvalues. Thus, the focus is mainly on determining the eigenvalues, and the other types of analysis will be dealt in the next further sessions. So stay tuned. Let us start with the session. Dynamic analysis is strongly related to vibrations. Vibrations are generally defined as fluctuations of mechanical or structural system about an equilibrium position. The vibrations are initiated when an inertia element is displaced from its equilibrium position due to an energy imported to the system through an external source. Vibrations occur in mechanical and structural systems. Without being controlled, vibrations can lead to a catastrophic failure. Vibrations of machine tools can lead to improper machining of parts. Structural failure can occur because of large dynamic stresses developed during earthquakes or even during wind. Excessive vibrations of pumps, compressors, turbo machinery and other industrial machines can induce vibrations on the surrounding structure. Before we completely understand the dynamic behavior of structures, let us understand the static part of it. During static analysis, it doesn't matter how you apply the load. It is assumed that the load is happening extremely slowly. This means that the way you apply the load has no impact on the structural behavior. The load is not changing in time, it is just there. Static analysis is much easier to calculate than dynamic analysis and requires less sophisticated equations. Let us now understand what exactly is static load equivalent or impact loading. In essence, if something will impact our structure, you may not have to calculate the actual impact. This is where static equivalent or dynamic load comes into play. The idea is very simple. Just increase the load with a dynamic factor or impact factor. Then you can treat this as static load in the analysis. The main difference between static and dynamic analysis is time. If the load is applied very slowly, that the inertia effects won't play a role. All we need is static analysis. Dynamic analysis is used to evaluate the effect of transient loads or the loads that change with time. Also, dynamic analysis will involve the analysis of vibrations and its effects. Let us now understand the different types of dynamic analysis. The first type of dynamic analysis is eigenvalue analysis, or simply it is also called as modal analysis. In this, analysis of normal modes or natural frequencies of a structure is determined. It is a method of finding resonant frequencies. By understanding the dynamic characteristics of a structure experiencing vibrations, we can prevent resonance and damage of the structure. During this analysis, the effect of load is not considered. The main objective of this analysis is to determine the natural frequencies and normal mode shapes. The next type of dynamic analysis is transient analysis. It is the analysis of a structure under time-dependent loads. In this analysis, the load will be the function of time. So clearly, the main objective of this analysis is to determine the response of the structure within a time domain. In this case, the load will be the function of time and the effect of load will be considered during the analysis. Another type of dynamic analysis is frequency response or harmonic analysis. In this analysis, the response of a structure is determined under sinusoidal loads. That is, the loads will be frequently applied and the frequency of loads will be studied on the structure. The response of the structure due to these loads are studied to determine the effect of vibrations. The most simplest representation of mechanical system under a dynamic system is a spring mass damper system. A simple mechanical system is schematically shown in this figure. The inputs applied to the system are represented by the force P of T. The output or the response of the system is represented by the displacement, and the system boundary, which is a region of interest in the analysis. What is outside the system boundary is the environment in which the system operates. Let us now understand completely how the spring mass damper system will help us to generate a governing equation which we will be using in dynamic analysis. Let us now understand the different types of vibrations. If there is no resistance to motion, that is, no damping in a spring mass damper system, then the vibrations will continue for indefinite time, and in such cases the amplitude of vibration will never change. And if the force is applied initially and later removed, then such vibrations are known as free vibrations. So in the absence of damper, then such vibrations are called as undamped free vibrations. If there is a resistance to motion, then the amplitude will reduce and such vibrations are known as damped free vibrations. The vibrations that occur under the influence of continuous force are known as forced vibrations. In such vibrations, the forces will be function of time. Let us understand the various forces involved in spring mass damper system. The equation of motion of a spring mass damper system or any dynamic system is as shown in the screen. It consists of majorly three forces: inertia force, damping force, and elastic force. The overall behavior of a structure can be understood through these three forces. Inertia force is generated by accelerated mass. Damping force describes energy dissipation mechanism. This force is known as general viscous damping force. The final induced force in any dynamic system is due to the elastic resistance in the system, and this force is the function of displacement and stiffness of the system. Such a force is also called as restoring force, or occasionally the spring force, or it is also called as elastic force. The applied load has been presented on the right side of the equation, and it is defined as the function of time. This load is independent of the structure to which it is applied. Let us consider a spring mass damper system without an application of force. It means we'll be discussing about the modal analysis where the effect of force is not considered and thus the applied force is considered to be 0 on the right hand side of this equation. Also, if the damper is not present, then this equation will be mx double dot plus kx is equal to 0. In this equation, m refers to the mass and k refers to the spring constant. This equation is similar to a simple harmonic motion where the displacement x is given by a sin omega t, where a is the amplitude of the movement or simple harmonic motion and omega is the circular frequency and t is the time. If we differentiate the displacement with respect to time, then we'll be able to determine the velocity, which is given by the following equation: x dot is equal to a omega cos omega t. Further differentiating the velocity, we'll get acceleration. The acceleration x double dot will be equal to minus a omega square sin omega t. In this case, the term a sin omega t once again represents the displacement. Thus, x double dot is given by minus omega square x. Substituting the value of x double dot, that is the acceleration, in the equation mx double dot plus kx equal to 0 will result in the governing equation of motion for a spring mass system without damper as well as without external force, and this equation is given by k minus omega square m multiplied by x is equal to 0. This equation can also be written in simple terms by using eigenvalues. K minus lambda m multiplied by x is equal to 0, where lambda is called as eigenvalue whose value will be equal to omega square. Thus, the governing equation of motion which we'll be dealing throughout this subject will be k minus lambda m multiplied by x is equal to 0. Here x represents the displacement of the structure. Let us now understand the importance of inertia in defining the dynamic behavior of a structure. In addition to stiffness matrix, inertia or mass is considered during this dynamic analysis, which is also called as mass matrix. Let us now understand the effect of inertia. On the left side, you see a static analysis where the rotation is applied to the handle. This is what would happen if you apply the rotation to the handle very slowly. This is known as static domain. The load is applied very slowly that you can basically ignore the effect of inertia. But on the right, the rotation is applied at a faster pace, which is known as dynamic analysis. Notice that at the beginning, the handle moves before the tip realizes that there is a movement to be made. Then the tip tries to catch up and the stuff begins to shake. Note how the rod vibrates even after the rotation is done. Such an effect can be really visualized, can be understood only with the effect of inertia. There are two types of mass matrices. One is called as consistent mass matrix and the other one is known as lumped mass matrix. Let us understand what exactly these mass matrices will have for us in case of dynamic behavior of the systems. Let us understand the lumped loads or lumped mass matrix. During the analysis, the lumped loads are considered to be concentrated evenly at the nodes. These are nothing but the distributed loads in a structure which are divided along the nodes of the element. The same thing what we have done to calculate the basic elementary equations during analysis of beams. Such loads are called as lump loads. In simple terms, it is understood that the load on the structure is divided or concentrated only at the point of interest, that is only at the nodes. Such a behavior is very easy to formulate and very easy to calculate. It requires very simple equations, but the results will be of less accurate. In case of consistent loads, it is understood that the mass is distributed over the entire span. That is, the entire mass is evenly distributed over the entire length of the beam rather than just being concentrated at the nodes. In this case, the same displacement equations which are used to formulate the stiffness matrix of the structure can be used to formulate the consistent mass matrix. The consistent mass matrix formulation will have more equations and require more storage space compared to lumped mass matrix, but the accuracy of the system will be much more better than the lumped mass matrices. This matrix will give the exact values of the frequency and mode shapes. Most of the commercial available softwares make use of consistent loads to predict the dynamic behavior of the system. Let us now derive the consistent mass matrix for a bar element. This is how the question can be asked for you. So we will be deriving an expression for a consistent mass matrix for a bar element. Let us consider a bar element of length L as shown in this figure. Let this bar element has two nodes, node 1 and node 2. Let N1 and N2 be the shape functions of this bar element. As we have already know it, the shape functions N1 and N2 are given by the equations 1 minus zeta by 2 and 1 plus zeta by 2 in natural coordinate form. In matrix representation, N can be given as N1 and N2 as well as N transpose can be given as shown in this representation. The consistent mass matrix for a three-dimensional system is given by the following equation. In this equation, rho represents density and n represents the shape functions of a bar element. Since it is a three-dimensional system, the interstructure will be within the limits 0 to v, where v represents the volume. But if it is for a one-dimensional system, since bar is a one-dimensional, the limits will change from volume to length. Thus, for a one-dimensional system, we can observe that the limits are between 0 to L. Also, the volume is given as area into length. Therefore, instead of dV, we have the value A into dx. This equation represents the consistent mass matrix in terms of global coordinates. Let us now convert the global coordinates in terms of natural coordinates. The relation between the natural and global coordinate system is given by the following equation. Zeta is equal to 2 into x minus x1 by x2 minus x1 minus 1. Here x represents the global coordinates and zeta represents the natural coordinates. On differentiating this equation, we will be able to get d zeta by dx is equal to 2 by x2 minus x1, which is nothing but 2 by L, where x2 minus x1 is nothing but the length of the bar element. Therefore, from this equation we can understand that dx by d zeta is equal to L by 2, or the value of dx is equal to L by 2 d zeta. Substituting the value of dx, that is L by 2 d zeta, in this following equation, we will be able to determine the consistent mass matrix for a one-dimensional structure in terms of natural coordinates. Now we'll be determining the matrix by substituting the values of shape functions. Before that, let us take out the constants outside of the integrals. So the matrix equation will be equal to rho a L by 2 within the limits -1 to +1. In this case, rho is called as the density of the structure, material, and A is called as the area and L is the length. Let's now calculate the value within the integrals. As we know that the value of n is n1 and n2, this matrix representation will be used in this equation. So substituting the values of n and n transpose in this following equation, will be getting the equation of this form. Now let us multiply these two equations to obtain a matrix. Note that this equation will be of the form, the order of this matrix is 2 cross 1 and the order of this equation is 1 cross 2. Thus after multiplication we will be getting the order of the equation as 2 cross 2. Thus this equation after multiplication is obtained as follows: n1 multiplied by n1 results in n1 square. Similarly, n1 multiplied by n2 results in n1 n2. Thus the other terms are obtained. Let us now start integrating each term. Let us integrate the first term n1 square within the limits -1 to +1. We know that the shape function n1 is given by the equation 1 minus zeta by 2. Therefore, substituting the value of 1 minus zeta by 2 in the following equation will be ending up in such an equation. The value of 1 by 2 whole square is taken as 1 by 4, and since it is a constant, it is taken out of integrals. On squaring the equation 1 minus zeta whole square, we will be able to get the value 1 plus zeta square minus 2 zeta. Integrating these values with respect to zeta gives rise to the following equation. Integral of 1 is zeta, integral of zeta square is zeta cube by 3, and integral of zeta is zeta square by 2. On cancelling the value of 2 and substituting the limits +1 and -1, we will be able to obtain the following equation. On simplifying the following equation, this equation will be having a value of 2 by 3. Thus, the first term, that is integral of n1 square in terms of natural coordinates within the limits -1 to +1, will result in a value of 2 by 3. This value can be substituted in this matrix. Let us now find the value of second term n1 multiplied by n2. Since we know the value of n1 as 1 minus zeta by 2 and n2 as 1 plus zeta by 2, simply substituting these values in the above equation can help us to determine the second term. So by multiplying the values n1 and n2, we will be obtaining this value 1 by 4 as a constant, which can be taken outside of the integrals. Since this equation is of the form a minus b multiplied by a plus b, the result of this equation 1 minus zeta into 1 plus zeta will be 1 minus zeta square. Integrating the value of 1 minus zeta square within the limits -1 to +1. Integral of 1 is zeta and integral of zeta square is zeta cube by 3. Thus, substituting the limits -1 to +1 will end up in having a value of the second term as equal to 1 by 3. Thus, the value of second term will be 1 by 3, which can be substituted in this place. Now, let us find the integral of the next term called as n2 square. We know that the second shape function for a bar element is represented by 1 plus zeta by 2. Substituting this value of n2 in the above equation will result in determining the value of the third term, that is integral of minus 1 to plus 1 into square d zeta. Since 1 by 2 whole square is a constant and can be taken out of the integrals. Now expanding the term 1 plus zeta whole square gives to 1 plus zeta square plus 2 zeta. Integrating the above equation will result in the following equation. By cancelling the term 2 and 2 and by substituting the integrals minus 1 to plus 1, we'll be obtaining the value of the third term, that is n2 square. This value will also be equal to 2 by 3. Thus, the value of 2 by 3 can replace this term into square. Once after finding all the values, these values are replaced in the following equation. So, thus the value of consistent mass matrix is rho L by 2 minus 1 to plus 1, and the multiplication of shape functions can be seen here. This multiplication of shape functions will result in a 2 cross 2 matrix, and by finding the value of each term and substituting in this elements, will end up in getting the value of m is equal to rho L by 2 multiplied by the matrix as you see on the screen. Now taking the value of 3 out common, the value of consistent mass matrix is given by the equation m is equal to rho L by 6 multiplied by 2, 1, 1 and 2. This is the equation for consistent mass matrix for a bar element. Let us now derive consistent mass matrix for a truss element. The truss element is similar to bar element except that one of the member will be inclined. Thus, the shape functions of the truss element will also be the same as bar element, that is given by the following equations. n1 will be equal to 1 minus zeta by 2 and n2 is 1 plus zeta by 2. Since the degrees of freedom of truss element will be more than the bar element, the shape functions in the matrix form can be represented by the following equations. The transpose of the shape functions is represented by the following equation. Let us now find the consistent mass matrix of a truss element. As discussed in case of bar element, the consistent mass matrix for a three-dimensional system is given by the following equation. In one-dimensional case, the equation is given by m is equal to density multiplied by the equation. Note once again that once the domain changes from three-dimensional system to one-dimensional system, even the limits will also change. Also, the volume dV is replaced by A into dx. This value or this equation is in terms of global coordinates. By finding the relation between the global coordinates and natural coordinates, the entire equation can be converted in natural coordinate system. Thus, by using the relation between natural and global coordinate system, we will be able to determine the value of dx in terms of d zeta. Substituting the value of dx in terms of d zeta will end up in the following equation. Thus, taking the values of the constants density, area and length, will be able to determine the value of consistent mass matrix will be as given by the following equation. As discussed in the previous procedure, let us now first find the integral of the limits nt multiplied by shape function n. By multiplying the matrices of shape function and its transpose, will end up in the equation as shown in this figure. This equation will also has basically three terms. One is called as n1 square, the second one is n1 and n2, and third one is n2 square. The other elements are repeated same as the previous elements. Let us now start finding each term individually and later substitute the values in the following matrix. The first term is integral of -1 to +1 n1 square into d zeta, as we know that the value of n1 is 1 minus zeta by 2. By simplifying this equation, we will be able to determine the value of integral of -1 to +1 n1 square d zeta as 2 by 3. This value will be substituted in this equation. Similarly, the value of the second term, that is n1 and n2, will end up the value of 1 by 3. Thus, the value of 1 by 3 will be substituted in place of n1 and n2. Now note that the entire procedure is same as in case of bar element. Now let us find the value of the third element or the third term called as n2 square. Since the value of n2 or the n2 is represented by the equation 1 plus zeta by 2 whole square, and on further simplifying, the value of the third term will end up in giving the value of 2 by 3. Thus, after finding the values of n1, n1 and n2 as well as n2, we'll be substituting these values in the following 4 cross 4 matrix. So thus, by substituting these values, we'll end up in the following equation. Taking the value of 1 by 3 common, the consistent mass matrix for a truss element will be given by the following equation. Let us have a small recap of the equations which we have discussed during dynamic analysis. The first and foremost part of dynamic analysis is the governing equation of motion, which is given by the equation k minus lambda m multiplied by q is equal to 0. In this equation, k represents the stiffness matrix, m is the mass matrix, and q is the displacement matrix. Here, the lambda is called as eigenvalue, which can be found and whose value will be equal to omega square, where omega is known as circular frequency. By finding the value of lambda, we can determine circular frequency, and also once we find the circular frequency, the frequency or the natural frequency can be determined by using the equation f is equal to 2 pi by. The stiffness matrix of a bar element is given by the following equation, and the stiffness matrix of a truss element is given by the following equation. We will be making use of these equations to determine the stiffness matrices during dynamic analysis. Also, we have seen that the general equation for consistent mass matrix is given by the following equation. This equation represents in a three-dimensional environment. The consistent mass matrix for a bar element is given by the following equation. M is equal to rho AL by 6 multiplied by the matrix. And for a truss element, this is the equation which we will be using. Also, the lump mass matrix for a bar element is given by the following equation. M is equal to rho AL by 2 multiplied by identity matrix. Thus, it is said that Using lumped mass matrix during calculations will be easy, but using the same lumped mass matrix will end up in an inaccurate results. Let us now discuss the basic procedure to find the natural frequencies as well as mode shapes using finite element analysis. The first and foremost point in performing the analysis is to convert the geometric model into finite element model. Once the conversion has been done, or during the conversion, one has to ensure that the structure should have minimum 2 elements so that minimum of 2 natural frequencies can be determined. Thus, a system having n degrees of freedom will have n natural frequencies. In the next stage, after converting the finite element model, let us now determine the stiffness matrix as well as the consistent mass matrices as given by using the previous equations. Substituting the values of k, m and q in the Gaussian equation will be ending up in finding the value of eigenvalue. To obtain the value of eigenvalue, let us now apply the boundary conditions and reduce the Gaussian equation using elimination method. Thus, if any part of the structure is fixed, then the corresponding row and the corresponding column of that element in the stiffness matrix will be eliminated. Once the equation is reduced, the eigenvalue lambda can be easily determined. To find the value of lambda, let us now equate the determinant of the equation k minus lambda m to 0. Once you use this, we will be able to find the values of lambda 1 as well as lambda 2. By using these eigenvalues, we can find the circular frequencies as well as by using the circular frequencies, we can find the natural frequency of the system. Let us now discuss the procedure to find the mode shapes. Final modal equations can be obtained by substituting the values of lambda 1 as well as lambda 2 independently in the following equation. It is customary to substitute the values of one of the displacements in this displacement term equal to 1 to find another displacement. Thus, you can understand from the following figure that if the value or one of the support is fixed, the value of Q1 will be 0. The value of Q2 is what we will be calculating using the procedure, and simply the value of Q3 will be equal to 1. Thus, by using this customary assumption, we can understand how the effect of Q1, Q2, Q3 will be there in case of dynamic analysis. Thank you friends for being here and witnessing the entire video session on dynamic analysis. In the next video, we will be discussing about how to solve numericals using dynamic analysis. Till then, have a nice day